All right. All right, so hey everyone, this is Daniel for Rock the JVM, and you are watching a live coding demo of what I would hope to be some artistic or creative use of the Scala programming language. Now, I'm pretty sure that you have your mind frozen or fried, depending on which side of the heat spectrum you are, by all the amazing talks today. So I'm not going to try to burn that brain even more. Hopefully this talk is going to be a more relaxing journey for you, not for me. And hopefully by the end of this talk, we're going to get some hopefully decent visual output, and we're going to fulfill every programmer's dream, which is to be able to build your own screensaver. We'll see how far we go. So this is my only slide. I'm going to simply run some live code, which is absolutely terrifying. But we're going to experiment with Scala.js in this talk. So can everybody see the code well? Does anybody have any? OK, seems all good. So what I have here is a little project in Scala.js where I have some values here that I've already set, and some magic functions that I'll hopefully get to in due time. And what I would like to create in this talk, hopefully my computer didn't freeze too much. Did it freeze? Yep, it froze. Anyone? I'm not seeing my own screen. Can we help? Nothing's working.
Can I?
Yeah.
Let's try that again. I don't know.
Yeah, now I can see it. Yeah, I need to rearrange my screens again. Right. Fantastic. Cool, back to the code. So in this talk, or in this demo, I'm going to draw things on this absolutely fantastic white screen on the left. So hopefully by the end of this talk, we're going to get some particles moving nicely, and we're going to have them moving in a dynamic fashion, meaning that their inputs are going to vary across time. So what I'm going to do first is on this JavaScript canvas, which is denoted in code by this display canvas in Scala.js, I'm going to draw some stuff. So in main, I'm going to simply run a little function that I'm going to call make. I froze again? Is it the HDMI? Do you need? Can I use any sort of a extra adapter or something?
Yeah. Let's try that to the USB-C.
Yeah.
That is strange.
No? Would you like me to fetch my own? I also have one.
I have some more here.
Yeah? If I had a guitar, I would play some absurd Ed Sheeran. And
Let's try that one.
even the cables are tired. Yeah, let me allow that.
Not really.
Not yet? Have another. I have one more. Do you want me to use it? No, that's fine.
All right, let's try this one.
I'm going to go try to fetch one. We're in between friends now, so it's fine. Can you use this one? Wow. Which one is it? Oh, it's... Why is it frozen again? Yeah. Mirror me. Okay. We have visual. Okay. So I'm going to define a little method called make good art, because if you are interested in commencement speeches and that sort of stuff, I recommend you watch Neil Gaiman's Make Good Art commencement speech. It's absolutely fantastic. So a little tribute to that. This make good art is going to simply create a magnetic field that is not going to be present on the canvas, but is going to direct the movements of some particles. And hopefully, depending on how we create that magnetic field, those particles are going to move in some interesting fashion. So what I'm going to do is, in this grid that I've created here at line 22 that hopefully does not freeze anymore, in this grid, I'm going to describe some angles. So in this grid is going to describe a kind of magnetic field that at every point is going to direct the movements of some particles. So what I'm going to do is, first, I'm going to create a random magnetic field so that you know how this thing looks like. So I'm going to run a very simple procedural for loop in Scala. I try to avoid the term for loop. So I'm going to have for 0 until, and I have a grid size of 100 by 100 of magnetic fields in this canvas. So I have an invisible grid of little arrows that were going to direct the movements of some particles. So I'm going to have 0 until grid size. And for 0 until grid size in underscore, I don't care about that. Maybe I do. That's going to be a row. And I'm going to have a column in, again, 0 until grid size. And I'm going to do the following. I'm going to say grid of row and column is going to be a math random. And the math random, you know, that's going to return a function of value between 0 and 1. But in terms of angles, I'm interested in values between 0 and 2 pi. So I'm going to have a math pi, and I'm going to multiply that by 2. So this is going to be a random value between 0 and 360 degrees, or in radians, that will be math pi. OK. So what I'm going to do is, in main, in make good art, I'm going to create a very, very random flow field. So this is going to be a function called make completely random magnetic field. And this make random magnetic field is going to run this for loop. And I'm going to run this make random field. And then I'm going to take all the grids here. So I'm going to have a for loop again. So I'm going to have for, let's call this row in 0 until grid size. And then call in 0 until grid size, more, I just copy that. And I'm going to run a little function that I prepared for this talk because it's so tedious, is to draw a little arrow on the canvas. Now, the drawing of arrow on the canvas just refers to the JavaScript API. So the JavaScript API takes what is called a context, which is a very rich data structure able to do a variety of stuff on an HTML canvas. So I'm going to just translate to these coordinates, rotate a bunch of angles, and draw some lines. So lines, and then the arrowhead, and then specify the fact that I'm going to draw the arrow in black, and then I'm going to say context.stroke to draw the path that I've just described. So what I'm going to do is I'm going to say context, which is the rich data structure that describes the absolutely fantastic, beautiful white canvas that you see here on screen. I'm going to say context.draw, or draw arrow, because I've just imported these tools. So I'm going to say context.draw arrow. I'm going to have row times. And row times resolution is going to be the size of the mini square that I'm dividing my canvas into. So row times resolution and column times resolution. And these things are going to be, my draw arrow function takes a length and an angle. OK, so the length is going to be my step length. I have a little variable here that I've absolutely set to a random variable, to a random value 3. And the angle is going to be grid at row and column. Just for you to understand how this thing works, so make good art currently will display a bunch of arrows, hopefully, on the screen. So I have my Scala.js, and I'm running this on localhost 1234. And look at these little arrows. If I zoom in, you can probably see them. So these look like fleas or bugs on the screen. But that's totally understandable, and that's totally relatable. OK, so this make random field now currently just draws arrows all across the board. Wouldn't it be nice if this make random field wasn't all that random? So if I turned on some particles and I left them on the screen, they would move in the directions of these arrows. So they would literally bounce around across the screen. But that's not really all that beautiful. We would love to create a random magnetic field such that the arrows that sit close together are not really all that different from each other. So we would like to create a function that returns very small variance or small differences for the output based on small differences of the input. So in mathematical terms, that would be a doubly differentiable function or a doubly partially differentiable function on the coordinates x and y on the canvas. Many such noise functions exist, and I'm going to use a function called Perlin noise. Now, Perlin noises aren't really rocket science. I have an implementation here. I wrote that myself. There are a bunch of libraries that do that just for you to understand how noise 2D works. This takes a bunch of coordinates. I called them x and y, but they can actually mean something different than spatial coordinates. One of the coordinates can be the brightness of a pixel, or time, or the position of some sort of other particle on the screen. So based on a couple of coordinates, I'm going to return a value between 0 and 1 with this property, that with a low variance in the input, I'm going to obtain a low variance of the output. That's the general idea, but the output is going to be random in a way. So what this Perlin noise does is, depending on how you want to interpret the coordinates of the Perlin noise, you can generate textures in video games, you can generate topography, you can generate water, you can generate all sorts of different random-ish things in real life. So I'm going to use this Perlin noise to generate this magnetic field that I was talking about. Now, I am going to hurry quite a lot. So I'm going to, instead of grid row call math random, I'm going to use my Perlin noise field, so Perlin noise 2D, and I'm going to use row times, and I'm going to scale that out. So I'm going to have a val scaled x, that's going to be column times 0.005, and val scaled y as row times 0.005. I'm going to use this noise 2D function on scaled x and scaled y. Now, if I run this function, notice that the arrows are nicely aligned together. Now, not only that, I'm not sure how easy you can see this, but the arrows do vary quite a bit. So notice that some of the arrows are horizontal, and as I scroll through the canvas, they change very smoothly. Now, if I run a particle and leave it on the screen, that's going to move in the direction of these fields. Now, the output of that hopefully is going to make more sense. Here's what I'm going to do. Instead of drawing arrows, I'm going to create a little function to draw some particles on the screen. Now, how am I going to represent particles? I'm going to say draw particles. So draw particles is going to take my particle trails, and I'm going to draw mini snakes on the screen. So particle trails is going to be a list. And every particle is going to also contain a list of positions where that particle has been across time. And these positions can vary across time, of course. So that is going to be a list of a list. Every position of the particle across time is going to be described by two things at least. So it's going to be a double-double. These are going to be the x and y coordinates. But not only that, but I'm also going to, for every segment in that snake, I'm also going to represent the age of that particular segment. So I'm going to have a list of triples, list of double-double int, and this is going to be a magical unit. Here's how this works. First, I'm going to create some particles. So let's get val particles, and I'm going to have a 1, 2, and I have a bunch of particles here, n particles. Amazing. This is very, very smart. So I'm going to have a map for every particle. I'm going to return a val, let's say x, as a math random times display width, val y as math random times display height, and an age. That is, I'm going to generate random particles at their particular stages in life, and I'm going to generate that randomly as well. So math random times, and I have a variable here that was, again, very smart, called max age. So max age. So that not all particles are generated at the same point in their life, so boom, all the particles on the screen, and boom, all the particles are regenerated at a later point. So I'm going to return these triples, so I'm going to say x, y, and age. Now, this thing is going to call render particles, So hopefully that would not render particles, draw particles. Draw particles with a list of particles dot to list because it's an index sequence of stuff, I think. So val particles, it's an index sequence. Draw particles list of double double int math random. Yeah, this is going to turn it to int because, of course. Right, so hopefully the code now compiles. A beautiful, beautiful piece of art here on the left-hand side. I want you to sit there and appreciate it. So in my draw particles function, what I'm going to do first is I'm going to obtain a position of the new particles based on the current head of this list. So the head of every single list here is going to be the position of the head of the snake. So what I'm going to do is I'm going to have a val new particles as particle trails head. And I'm going to have map. And in case we have an XY age, I'm going to do the following. First, I'm going to have a row into which that particular head is going to be associated. So that's going to be y divided by, it's called resolution, and then to int, and same for the column. So val column is going to be x divided by resolution, and then to int. So these are going to be the grid boxes in which that particular position is being allocated. Now, I have to respawn the particle if the particle somehow goes outside the scenery, the beautiful canvas here on the left-hand side, ladies and gentlemen. So I'm going to have an if statement here. I know that if with parens are not that fashionable anymore, but I'm not going to care about that. So I'm going to have if the row is bigger than or equal to 0, and row is not bigger than the grid size, and at the same time for column is bigger than or equal to 0, and column is less than grid size, and also age is less than max age, I'm going to return the natural position that this particle will move, which is the case that x and y now becomes x plus a direction given by the magnetic field at that position, which is row col, and y plus whatever. So I'm going to return the following tuple, x plus. There is a variable here that in my absolute wisdom I called step length. So x plus step length, and I'm going to multiply that by the cosine of the angle described by the magnetic field at that point. So this is going to be the angle. So val angle is going to be the grid at the row and column. And I'm going to have x plus step length times cosine of angle. For those of you who need to brush up your physics, contact me tomorrow. I'm going to have x plus step length cos angle, y plus step length times sine angle, and then age plus 1. So this is going to be the next line in the snake's trail. Otherwise, I'm going to have to respawn that. So I'm going to have a math random. So I'm going to have let's say new x, new y, and I'm going to return new x, new y, and starting at 0 because the particle is respawned somewhere else. So these are my new particles. Now, before I draw them, I'm going to fill the beautiful canvas here on the left-hand side with another beautiful color, which is absolutely black. So I'm going to have context.fill fill style. I'm going to have a CSS color which is black, and then I'm going to say context.fillRect 00 display width, I think it's called, width, and display height. So I'm going to fill the canvas with absolute pitch black. So I'm going to do that. Look at that. The whole room went black, dark. So that was quite effectful. So we have these new particles. Now, what I'm going to obtain is the new particle trails. Now, because the particle trails currently has just one position for every particle, I have to check whether the particle trails has more segments than one. So I'm going to have my new particle trails as, and I'm going to have an if statement with the unfashionable syntax here. If the particle trail's length is bigger than max age, then I'm going to have particle trails.init, thereby cutting out the last segment of every snake and prepending that with my new particles that I've just spent so much time computing. Otherwise, I'm going to have my new particles prepended to the particle trails. Okay, so these are the new snakes, essentially. New snakes. Now I have to draw them. How on earth am I going to draw them? Because the particle trails themselves are just collections of positions, but I need to draw lines, which means that I have to combine the positions with the previous positions, which is why I'm going to write a pretty complex construct here, which is going to be new particle trails init. So that's going to be the new positions, zip with new particle trails dot tail, that is the old positions, zip with index, and then I'm going to have a for each. And I'm going to have a case for, and this is going to be a nested tuple, so this is going to be new particles, or new positions, new particles, and old particles, and the age of those particles. Now, new particles and old particles may have been respawned at that point. So depending on whether the particle has just exited the stage, the particle is going to be respawned at some place random, and I don't want to draw a line across the screen, which is going to absolutely destroy my beautiful canvas. So what I'm going to do is I'm going to say new particles, zip with old particles, and then I'm going to filter that, and in case we have a tuple of two tuples, so we have new x, new y, and age, and x, y, and age. I don't care about that. All I want is to be sure that these two things are not across the screen. Now, how am I going to get that particular conclusion? Well, new x and x, if the particle moves normally inside the screen, they're always less than step length. So the abs of the difference between new x and x is going to be less than the step length of every segment. So new x minus x is going to be less than or equal to step length, and math abs, because I forgot to call the function here. So math abs is between new y and y is going to be less than step length as well. Come on, compiler, keep track. New y minus y. All right, thank you very much. So after that, after I filtered the lines of the snake that I'm going to draw, I'm going to run a massive for each. So for each case, and I'm going to have a similar kind of tuple here, nested tuple, new x, new y, and age. X, y, and the old age, that's going to be age minus 1 naturally. I don't care about that. I'm going to say context.beginPath. And I'm going to start a procedural way of drawing a simple line on the screen. So I'm going to have context.fill, not fill, stroke. Stroke style is equal to a CSS class, which is going to be a pain in the ass to create, but I've created one for you, which is called lerp color fade, lerp from linear interpolation. Linear interpolation is going to take a value between 0 and 1 and between two colors, A and B, described as CSS colors as hexadecimal integers. So I'm going to do the regular bit shift, and I'm also going to fade out the lines by adding a little alpha channel. So I'm going to have a lerp color fade, and the item that I'm going to pass inside as the value between 0 and 1 is the age of the segment, which is going to be age times 1.0 divided by max age, and I'm going to have two CSS colors that I'm going to just make up. For example, 0x, and I'm going to try a blue one, so or a cyan, maybe. So 0080FF, so the blue, 0x08000FF. Hopefully that will look half decent. So stroke style, context, stroke style, not stroke style. It's going to be a width, line width is equal to 1, context, go to, or move to, yeah, x and y, and then context line to, new x and new y. And then context dot stroke, which is going to draw that particular line, and that's going to be it. So I've computed the particles, I've drawn them. Hopefully I didn't make any absolutely idiot mistake. And at the end of the day, what I'm going to do is I'm going to request a new animation frame via a very weird JavaScript function, which is called DOM window request animation frame. This is going to take a callback, which Scala.js has very dutifully abstracted away as a lambda. So I'm going to say render particles with the new particle trails. So not render particles, it's called draw particles. Amazing. Look at that. So you have kind of like a shooting star here, but the shooting stars are like in reverse because apparently my alpha is t. Maybe if I change it to 1 minus t, yeah, look at that. So the interesting thing is that every time I refresh the page, the Perlin noise is different. So the magnetic field goes in different directions. And at this point, I think, my friends, you can generate your own screensavers. Now, if I do the step length is equal to 5, and I create a bunch of extra particles on the screen, the flow is going to be a little different. Maybe if I create like 1,000 particles, look at that. If I do 5,000, yeah. Well, you can play with these parameters. I'm going to share the code on GitHub anyway. So yeah, I think this is pretty nice. Now, this Perlin noise can also have a third dimension. Do you have like extra 5 minutes? All right. I can also vary the Perlin noise, which it describes the flow fields of this beautiful canvas. I can also vary that across time or with an extra dimension, which is why in my draw particles method, I'm going to call the makeRandom field every time. So instead of calling the makeRandom field once, I'm going to call that on every frame. Now, this approach is not going to win any performance contests, so don't yell at me because of that. But computers are quite powerful, and these fields will be created on every frame without any sort of problems. Now, the interesting thing happens when the random field also has a third dimension, which is, for example, maybe time. So in makeRandom field, I'm going to have my time as date.now, and I'm going to multiply that by a very small number, like 0.0005, or something like that. And instead of noise 2D, I can create a Perlin noise 3D, which for a volumetric thing like a spatial coordinate Perlin noise, you can generate volumetric smoke in video games, which is quite interesting. But the third dimension may not necessarily be a spatial coordinate, but something that relates to time, or something that relates to anything else but space. So maybe I'm going to place in time here, and I'm going to use, instead of Perlin noise 2D, I'm going to say Perlin noise 3D. Now, if you wait for a little bit, these fields are going to change in time. If you look at that, look at that. See? So these fields can also change across time. And at this point, you have a dynamic wallpaper or a screensaver that you can look at. Now, depending on the values that you place here, I've chosen 0.005 because I played with this code for days before I came here to talk. So these values here seem quite magical. If you want to, give me 5 minutes, please. Come on. Come on, man. All right. So if you want to increase the input or the weight of one of these coordinates, you can scale these to something more drastic. For example, maybe if I double these, the Perlin noises are going to be much more interesting. So look at that. So if you change this to 0.02, for example, the Perlin noises are going to change across time and also across space. So some of these rivers that you see here on the screen also get destroyed, or then they get reunited, or they get destroyed again. And so you can look at this for days and not see the same image at any one point. I'm going to take the liberty of taking a screenshot here. Okay, now, because I knew I wouldn't have time to generate a more special flow field than the time-generated one, I'm going to call another function which is called makeSpecialFlowField. This thing is a little bit more involved, but it's not that rocket science. What I'm going to do for the third dimension of Perlin noise is create a brightness pixel captured from the webcam instead. So I'm going to call this makeSpecialFlowField instead, and in my makeGoodOr main function, I'm going to call another magical function here which uses a very weird JavaScript API that I wouldn't know by heart, which is why I prepared it for the talk, which is startVideoMagic. So startVideoMagic is going to start getting input from the webcam, and that webcam is going to influence the position and the direction of these magnetic fields that I was talking about. Now, the interesting thing is that the Perlin noises that you see here on the screen are continuous, that they flow nicely. So the variations in output are proportional to the variations of the input. But because the webcam doesn't really have this sort of property, you'll also see some edge detection along the way. So if I save this file and refresh the page and allow this time to get some input, I get some really nice stuff. So I just prepared, I want to see my face. Well, it depends. Sometimes it's nicer, sometimes it's rivery. Now, I prepared a little writing here which says Scala rocks, and I'm going to place it here. So